Good afternoon. Good afternoon, everyone.
Will be delegated to the other parts.
Hang on, he's here.
Hey, Sam,
Good afternoon, Dr. Domochowski.
is it nice and warm in New York as well?
Yeah, I'm in your office right now working with Tariq to prepare
Nice.
the shipping boxes.
I recognize. Yes.
Yeah, do
Very
you miss your
nice.
office?
Yeah, very nice. How is the shipping going?
We are packaging the box. Do you have anything to say to him?
So packing is going well. Shipping domestically.
Recording on superposition, source transformation, Thevenin and Norton. These are all topics that will be on the midterm exam. The midterm exam will have 4 problems. And as I've said before, mesh analysis, nodal analysis, Thevenin analysis, Norton and or op amps. You will see super nodes, you will see super meshes. Problems at the back of the book are good practice. Homeworks are good practice.
Oh yeah, speaking of homework, like I graded your first homework and your second homework is halfway through. So just some note, please show all your work. Like if you just write out the answer, I cannot give you credit for that. Like if you got the right answer, I will just give you 1 point for each right answer, and it's not that much at all. And like as long as you show your work and you do all your calculation, even if you arrive at the wrong answer, but you set up the equation correctly, I will give you 90% of the point for that. So don't worry about like doing the wrong calculation. Just show your work, just to make sure that like you actually know what you're doing. Even if it's really obvious, just write at least 1 or 2 lines into that. And yeah.
Yeah, totally agree.
Yeah, like that exactly. You can just set up the equation, or like if you want to show like that you actually do some type transformation, you can just set up the matrix and you can just write out the answer using your calculator.
Yeah, but it's important. The work that you need to show in this class is how you get to the matrix equations, right? You
Yeah.
got to go from the circuit to the equations. We don't care, we trust that you know how to solve equations, but systems of equations, but you have to use circuits principles to derive those equations in the first place.
Like if you set up the equation correctly, you got like 90% of the point. The 10 point is just you do the calculation, doing some transformation, and like yeah, I'm really easy on that.
Okay, and let me quickly, there is one issue that because the exam, the midterm exam will be, you'll be writing it at your home, at your desk, wherever. And there's the issue of webcams. And I want to, well, I'm just going to do a poll. I'm not going to even bother. I'm just going to ask you. I will be asking, you guys don't like to turn your camera on during the lectures. That's fine. But on the midterm, we do need to see you writing your exam. So if there is anybody that has objections to that, please let me know immediately. This is one of these areas where there's been a lot of discussion. Okay, yeah, I know, but there's been a lot of discussion. Oh, we got a question from Omar. Yeah.
I just had a quick question because the way like I solved the system of equations was putting them in MATLAB. Would that still be possible with the cameras on? Because it's gonna like,
oh, you don't have
looking.
to, yeah, it's a good question, but it's not going to become you're not going to be asked to solve any, as long as you get the matrix. So on the exam, I don't ask you to solve the system of equations. I just ask you to write the system down.
Okay.
Yeah, I don't want you that I don't, the only thing I care about is that you apply the correct circuit laws, so KCL, KVL, etc., and derive the 3, 4, 5, or 6 equations. Just kidding, probably 3 or 4. But I don't ask you to actually solve during the exams.
Okay, thank you.
Oh,
Yeah.
yeah. For the homework also, please check your work. Please double check your work before, like even after you submitting, because like some students were missing the first page or the last page of their homework on Blackboard. And even if you don't get to like submit it on the deadline, just submit it after the deadline. The policy is about 10 pound off per day. And yeah. So like if you're late, just submit it, get some point, it's better than nothing.
Okay. Yeah, totally agree. Check your work. It's good practice for the real world, as they say. Yeah, so the midterm, you'll need to turn on your cameras. The exams, they're the only the only 2 lectures that I see you guys are the midterm and the final. Yeah, let's see. No, it's not open book, but trust me, you don't want open book. Open book exam means I have to make it very hard. So I can't ask you simple things if it's open book, right? And it wouldn't even help you. Like, I don't even know if the open book would help you much, because you have the circuit in front of you. You know what technique you have to use because it's specified in the instruction. So there'll be a circuit and you will say nodal analysis, and the circuit will have a supernode. And so you have to apply the laws of nodal analysis of supernodes. I don't know how much an open book exam will help you. Is it similar? I don't know. I never know how to answer that question. I don't yet know where I want you to point your camera. I know Professor Para likes. So to your question, Omar, I'd say that we the homework questions are meant. Some of the homework questions are meant to challenge you and require a lot of thinking. So in some sense, the exam will be easier than the homework, but in another sense, I like questions that require you to think, but they don't require too much mathematical, too much algebraic manipulation. So they'll still be challenging, but they're not going to require you to, stare at it for an hour before you even can know how to begin. So I don't yet know whether I want you to point your webcam to your paper or your face. I don't know yet. Someone's unmuted. I'm gonna mute you. Yeah. There was an email that went out last week about something called some kind of a browser lockdown system. I haven't researched it, but we may be using that. I don't know yet. I haven't researched this technology. Okay. I believe we are ready to begin. The Thursday lecture, I like to end early because I don't quite have the stamina to talk for 2.5 hours. Okay. The good news is that, like I said, lecture 6 is easy. And the part that we're doing today is really easy too. Yeah, I can suggest some supplementary questions before, let's see, I'll say 2 weeks before the midterm. I'll probably also share a previous midterm
Yeah,
much
also
similar
feel free
demise.
to, oh, sorry. Yeah, feel
Go
free
ahead,
to
Sam.
bring, yeah, feel free to bring the question into my office hour, or like you can just schedule another office hour time with me. And we can work through the problem together.
Let me just see if I can, oh, Max with, I got a new computer and ah, see if I have a previous. Midterm from 2016. So I'll show you 2016's midterm. Okay. These are the short answer problems. And then these are the circuits. Mesh analysis. You see it has a super mesh. Here is a Norton-Thevenin problem. And here's an op-amp problem. I showed one of these exams to my daughter, who's an engineering student. She said it was too easy, but I think she's just showing off. But that's kind of what you're in store for. Like, they're not, it's all doable. Like, the most, honestly, what I always say to people, go to the back of the book and do as many problems from the back of the book as you can. And I honestly think that the more questions from the back of the book you'll do, the better you'll do in this course. It's just, I don't think they're reading the slides. I mean, you have to read the slides to orient you and to kind of understand, foundational concepts. But it's not a course, and I think I made this mistake when I was a student. Some points, there's no substitute for cover up the solution and try to reproduce it. There's no substitute for that process. And that's what you should devote your time to doing it, to prepare for this midterm. Just do as many problems as you can. If you do that, you'll get an A, and most likely. Okay, so capacitors, just like resistors, and just like we'll see with inductors, can be combined either in series, which means that they carry the same current, or in parallel, which means that they have the same voltage, right? So basically, the rules for combining capacitors are opposite to those of combining resistors, meaning that capacitance adds linearly if they're all in parallel, and if capacitors are in series, you do the reciprocal rule, and you'll see that in just a second. So let's look at this circuit. We have a current source that's connected to a bunch of capacitors in parallel, C1 through Cn. Everything here is at the same voltage V. And we are interested in reducing this circuit to this one. So these N capacitors are in parallel, and we hypothesize they can be replaced with a single capacitance CEQ equivalent. So we know that this current I, the current that comes out of the current source, has to be split up into the sum of the individual branch currents. Okay, so I is equal to the sum of I1 plus I2 through IN. Notice that each of these currents is equal to the current through a capacitor. And we know that the current through a capacitor is equal to what? What's the expression for the current through a capacitor? Not even an answer on the chat? Yes, thank you, Christian. C dV dt, right? And the V here is the same for each of them, right? That's the important thing. The dV over dt term, because they're all the same voltage, can be factored out. Right? The dV over dt is factored out, and what you're left with is the sum of capacitance. And so the current I here is equal to the sum of capacitances multiplied by the derivative of V. In other words, the equivalent capacitance for n capacitors in parallel is their sum, right? So it's exactly the rule for resistors in series. So capacitors in parallel is the same as resistors in series. Very simple. Okay, hopefully that's clear to everyone. And now let's move on to the other case where the capacitors are in series. And again, we seek to reduce these n capacitors that are now in series into a single capacitor, CEQ. So now the thing that's common to these capacitors is the current. They all share the same current. And so let's write the KVL expression for this circuit, right? So we have V, the voltage rise V, has to equal to the sum of the voltage drops V1 plus V2, etc. And each of these V's is the integral of a common current, right? So we know that the voltage across a capacitor is equal to the integral of the current divided by the capacitance. So this integral factors out, right? This is a common factor here. And that's multiplying a sum of reciprocals. So we've seen this before when we were combining resistors in parallel. We saw sums of reciprocals. So just like with resistors in parallel, the equivalent capacitance of n capacitors connected in series is equal to the reciprocal of the sum of reciprocals. It's hard to say in words, but I think this equation is very intuitive, right? So again, they reduce in the same way that resistors do in parallel. So resistors in series, capacitors in parallel have the same rules, and capacitors in series, resistors in parallel have the same rules. These terms here are just the initial. Oh, we have a question. Go ahead.
So that means we can use the, you know how like we have the resistance rule for like just two parallel resistors where you multiply on the top
Yep.
and you add on the bottom. You can do the same that for capacitors.
Exactly.
When you
That's
have
actually, that's a perfect segue into, I think it's on the next slide. Yeah, exactly. It's the same, it's exactly right. So if you have two capacitors, it reduces to product over sum. And so these terms here, what makes this derivation a little bit messy. It's just that we have these initial voltages, but usually those will be equal to 0, in which case you ignore them. But don't worry, that's just because the initial a capacitor can come preloaded with an initial voltage. So that's why we have to include these terms, these V's at T0. Okay. Yeah, that's right. Capacitors in, so two capacitors in series, their equivalent capacitance is equal to their product divided by their sum. For two capacitors in parallel, their equivalent capacitance equals to the sum of their capacitances. All right, so these are easy. We can fly through these. So we are going to want to compute the equivalent capacitance as seen looking into the circuit from terminals A and B. So remember, we're looking from the right, so we want to start from the left. So how do we combine the 20 microfarad and the 5 microfarad? I'll give you guys virtual chocolate if you answer this. Yes, thank you. Is there a chocolate emoji I can throw in? So what is that?
I think that would be the poop emoji.
No, yeah, I'd love to, and believe me, I'm very immature, but I will not do that on the record. So yes, 20 and 5 will combine into a 4. So what about this is now a 4, and that's in parallel with a 6, and in parallel with a 20. So how do I reduce the 4? Let's see if you guys got it. Yes, excellent. You guys are very fast. 30 is correct. And then the 30 in parallel with a 60, as you probably know, it's 20, right? So the equivalent capacitance of this network of capacitors is 20 microfarad. Yeah, so the 20 is in series with the 5, right? But the rules for reducing capacitors is the same as the rule for reducing. So combining capacitors in series is like combining resistors in parallel. So it's product over sum. So these two are in series. Yeah, okay, good. What about this one? Who can help me reduce this? Yeah, you add in parallel. So where do I start with this one? Which two capacitors can I reduce?
Uh,
Go ahead, Omar.
going over. So I guess we could add the ones on top first. That would just be 120 microfarads.
Yep.
And then you would do the 120 microfarads. You would do that in parallel with the 20 branch.
No. Or I don't think. First you want to reduce the 60
And 120.
Yeah, the 60 and 120.
Oh, okay.
So that becomes that's 720 divided by, that's 40. 40, and then the 40 is in parallel with the 20. Yes, Andre, 70 farad, that's a mistake. I blame the book. I blame the graduate students that they hired to proofread the book on the sheet. So that should be microfarad. So yeah, we have 60 and 120. That becomes 40, and the 40 in parallel with the 20 becomes 60, right? So we have the 60 in series with a 120. So that should get us to, if I did it right in my head, it should be 40.
24.
Like this. Right, so we started off with, like you said, the 50 and the 70 become 120. This 60 and 120 become 40. The 40 in parallel with the 20 becomes 60. And then we have this, all of this together is 60, and all of this together is 120. So they're in series. So they product over sum gives you 40. Does anybody have questions with what we've done so far? Yeah, no, Ahmed, that's a typo. I guess I could have fixed it on my end too, but that should say microfarads. We'll never ask you. 70 farads would be like an abnormal, a very large capacitor. It's okay. You don't get those kind of capacitance values, maybe in like power lines. I don't know what the kind of, how strong those capacitors, but you know, micro and pico, those are what you see in the lab. All right. Oh, I like this one. I like this one a lot. For this circuit, find the voltage across each capacitor. So how do I begin this? What's the, remember, I'll annotate this with my, the rule is, oops. What is it? I guess the equation we want to use here is Q C P, right? And so first of all, what I would recommend is that we start off with combining these two. Yeah, yeah, I think that's a good idea. Yeah, we can. I like it. There's a debate on the chat. Yeah, voltage. Yeah, so you can do voltage division with capacitors, but that's definitely the right approach. It's just you cannot strictly apply voltage division here because these are now resistors. Let's see. The Numax have not. Give me a second here. Numax, same problem. Unbelievable. My cursor is gone. Let me see. Clear all. Yeah, so why is my doc here? Anyhow, I'll live with it. Yeah, so but first, before we do KVL, somebody made a good suggestion on the chat. It was, can we reduce it to a single capacitor? So Christian, that's the right, that's where I would start, right? So what is the equivalent capacitance of this circuit? So which capacitors are in parallel and which are in series?
The 40 microfarad and the 20 microfarad are in parallel.
And so they combine to
60.
60. Oh yeah, sorry. Yeah, I think somebody already answered that. I didn't mean to ignore that. Yeah, so that becomes 60, and then the 60, then 20, and the 30 are what? They're all in
Series.
series. So that's going to be 60 in parallel with 30 is 20, and then 20 in parallel with 20 is 10, I believe. Let's see if I did it right. Yeah. So the CEQ is 10. Thank you, Ahmed. That's right. So we know that the equivalent capacitance is of this circuit is 10 millifarad. And so my question to you now is, how do I say this? Again, this is a challenging example, first of all. So it's meant to make you think. So charge behaves like current. So in fact, current is just amount of charge per unit time. And so let's figure out for the, so this circuit, another way of, if that's not satisfying to you, let me just draw this circuit now. We have the battery. We have one capacitor that whose value is 10 millifarad. And this is 30 volt. Okay, so my question to you is, how much, yes, excellent. Yes, use Q is equal CV, right? So Q is the product of capacitance and voltage. And so what's the product? So, and we want to use the equivalent capacitance. So we want the total charge that's sitting across that capacitor. And that's going to be equal to what? Yes, that sounds right. 300 microcoulomb sounds very correct. Let me see if that is in fact. Okay. 0.3 coulombs, which is indeed equal to 300 microcoulomb. Okay, so now we have the total charge. And here's the key point. That total charge is distributed between these three capacitors. Okay, give me just 1 second. How do I do this now? I clear this. Close the chat. Try hitting escape. Okay. So that total charge is distributed among these four capacitors, right? We need to find the voltage across each capacitor. So we need to know how much charge is on each of these. So think of it this way, charge behaves like current, right? So every electron that comes out of this battery is going to have to flow through this capacitor and flow through this capacitor, right? And so and flow through the combination of these two capacitors. And so if you treat charge like current, then these two capacitors will see all of the charge that's being generated by this battery here, right? So V1 is going to be equal to Q1 over C1. Is that right? Q is equal to CV, so V is Q over C. So we have a, yeah. So charge is current is just charge, but measured per unit time, right? And so charge follows the same laws as current. So if these two capacitors will see every bit of current that's coming out of this battery, and so they'll sense all the charge coming out of this battery, which we know is 0.3 coulombs. And so these two capacitors effectively see or experience 0.3 coulombs of charge, right? And so V1 is equal to that charge, 0.3, divided by C1, which is 20 times 10 to the minus 3. And V2 is equal to that total charge Q over C2, which is 10. So V1 is equal to 15 volts and V2 is equal to 10 volts, right? Because again, current is just charge. So charge behaves just like current. And in the same way that these two capacitors would see all the current that's coming out of this battery because they're in series with it, they will experience all of this 0.3 coulombs of charge. So another way of stating that is that when they're charged, they will each have a charge of 0.3 coulombs. Okay, good. Okay, so now we have a 15-volt drop across V1 and a 10-volt drop across V2. So what is going to be the drop across these two? Right? What is chat answer? 5 volts, exactly. Very good. So we know the remaining 5 volts has to be passed across these two. And so that's basically it. Then we know the answer. We could have also reduced these two capacitors into a single capacitor of 60 and figured out using the V equals Q over C formula. That would have gotten us the same answer. But it's not necessary. You can just use KVL here. Remember, KCL and KVL always hold, no matter what. These are the two rules that you can always apply to any circuit. All right, I think this one is actually easier from what I remember. We are asked to find the voltage across each of these capacitors. So let's do the same thing as last time. Let's figure out the equivalent capacitance of this circuit. Who can tell me the 60 and the 30? How are they connected?
Series.
In series. Thank you. And so, oh, that's Siri. You're never there when I need you. When I don't need you, you're speaking up, Siri. So 60 and 30 are in series. And so how do you combine their values? 46, 20, right? 60 times 30 over 60 plus 30, 20. And then the 20 and the 20 are in parallel. So that gives us 40. And then the 40 and the 40 are in series. So that gives us 20, I believe. I did that in my head. I may have made a mistake. Let's see. 60 and the 30, 20. 20. Yeah, all good. 20 and 20 are 40. And then the 40 and the 40 are 20. Okay. So that's the total capacitance. The equivalent capacitance of the circuit is 20 microfarads. So what does that mean for the total charge that's generated by the battery? Sounds right? 120 microcoulombs sounds right. 1200, yeah, sorry, 60 times 20 divided by 1,000. So that's 1200 divided by, let's see, 1.2 microcoulombs. And so all of that charge this capacitor will experience all of that charge because it's in series with the battery, right? So we can just take this charge and divide it by C1 to get V1, right? So 1200 millicoulombs divided by 40 microfarads gives us 30 volts. So V1 is equal to 30 volts. Okay, so now we have to deal with the harder part of figuring out V2, V3, and V4. V2 is actually the easier of the two. What is V if the battery is 60 volts and V1 is 30 volts, what is the value of V2? Excellent, 30, right? So we're done with V2. Okay, so now we have to deal with V3 and V4. So V3 and V4 will have the same charge because they are in series. The question becomes what that charge is, right? We know that together they experience, so if you take the voltage between this point and this point, so V3 and V4 combined have to add up to 30 volts, right? Because this point to this point is 30 volts. And so this point to this point has to be 30 volts. So together they have V3 plus V4 have to add up to 30 volts. But we don't yet know in what proportion they're going to add up to 30 in. So let's see. Right, so that far we know. The voltage across the combined 60 and 30 microfarad capacitors have to equal to 30 volts. So the way to approach this is to combine these into a single capacitor. So the 60 and 30, so these two capacitors, 3 and 4, may be combined into a single 20, as over here. And then we can apply Q is equal to C times V to get that the charge that they will each experience is equal to 6 times 10 to the minus 4 coulombs, which I believe is, what is that? I'm drawing a blank, hold on, multiply it by 1,000, you get 0.06 millicoulombs, I think, or 0.6 millicoulombs. In any case, take that value and divide by C3 to get V3, right? Because these two capacitors, they both experience this much charge because they're in series, right? So what we did is combine these two into a single capacitor, figured out, knowing that combined they experience V2 is equal to 30 volts. From that, we figured out how much charge they each experience. And then we take the charge and divide it by the C, Q over C, to get the V. Q over C to get the V. Sounds like rhyming about circuits. I know that these problems are a little bit tricky, so feel free to ask me questions now. So how we're proceeding here, right? We figured out the charge that each of these capacitors experiences, and we divided by the capacitance to get the voltage. So V3 is 10 volts. And you already know that if V3 is 10 volts and V2 is 30 volts, then V4 has to be 20 volts, right? Because of KVL. So notice that the voltage across the smaller capacitor is higher. Fun little fact. Okay. Gonna rest my voice for just 1 second and see if you guys want to ask me any questions before I proceed.
Hey, Professor,
Go ahead.
could you just explain the second to last line one more time? Because I followed everything you said about finding the capacitance and combining the two. But
Good.
I'm just unsure where you got the current from, the charge from, yeah.
Yeah, so let me see. What I'll try to do is, hold on. Stop sharing for just a second. This is where a blackboard would be good. Okay, so basically that second last step is right. And so we basically replace. So this capacitor models this combination of these two. This is actually 20. And we know that the voltage here is, we got it here, it's 30 volts. So we know that the charge that's coming into here, that Q here is equal to C, this CEQ, which I'm just gonna call it C34 because it's the combination of capacitors 3 and 4 times V2. Right, so that's the V2 and that's C34. And that gives us 6 times 10 to the minus 4. So now we take this circuit and we expand it back out to the original. I'm just going to draw this part. We have, oops. Sorry, very messy. Right. So this here is this capacitor, and it has a charge of 6 times 10 to the minus 4. And then this capacitor here is this capacitor, which also has a charge of 6 times 10 to the minus 4. And then we just use the Q is equal to C times V rule to figure out their respective voltages. Hopefully that makes sense. I'm going to clear everything. You're welcome. Let me now go back to slideshow. We've done this one. Inductors. So we're moving on to the latter half of this lecture, which is on inductors, which is kind of an analogous circuit element to capacitors. So one way of thinking about a capacitor is that, you know, a capacitor, if you apply a battery across a capacitor, that capacitor will charge. What that means is that a charge will accumulate across the plates of the capacitor. And then when you remove the battery abruptly now, you'll get a transient current. So you'll get charge flowing through the capacitor. That's called the capacitor discharging. And so the way, I don't know, I always taught this in high school, capacitors charge and discharge. I don't particularly find that to be a very helpful way of understanding capacitors. It's much more, for me, it's much more helpful to understand that the capacitor is basically sensitive to a change of voltage across the plates. And it responds to any change. It doesn't just have to be on off. We have a visitor to the class. Come on in. I hope you're not a Zoom bomber. Okay. So inductors are like that, except that inductors, they're just like a coil, as you'll see, a coil wound around the solenoid. So something that's magnetic. And what happens is as that current's flowing around that solenoid, you get a magnetic field that gets built up. And if that current stops flowing, then that magnetic field all of a sudden will get released to the circuit in the form of a voltage across the coil, right? So whereas capacitors have a charge phase and a discharge phase, inductors have, you build up a magnetic field and then you release it in the form of a voltage. So it's a passive element that stores energy in the magnetic field. So they're used, I guess, in all these electromagnetics and electric motors, TVs, transformers. They're bulky. That's kind of the one distinguishing feature between a capacitor and an inductor. Capacitors can be made to be very small. They can be miniaturized. That's not really true for inductors. Inductors, in order to generate an appreciable level of inductance, you have to make them pretty big, and so you can't really, print them as integrated circuits. So kind of the classical inductor is a core material, so like iron, for example, something that's ferrous, and a conductor that's wound around that core. So we have a length of the core, we have its cross-sectional area, and we have the number of turns that the coil makes. And so what happens is you pass a constant current through that coil, and all of a sudden you get a magnetic field built up. And so the voltage that forms across the coil, so across the terminals of that inductor, is proportional to the change in that current. So in other words, if the current that's flowing through it is constant, then there's no voltage, and this element here just acts like a piece of wire. There's no voltage drop from one end to the other if the current is flowing through the coil is constant. But as soon as you change the rate of, you change the amount of current, then you get a voltage that forms transiently. And so the relationship between the change in the current and the voltage that forms across the core is equal to the inductance. And it's named after Joseph Henry, who apparently was an American inventor. And so if you change the current by 1 amp per second, and you get a voltage of 1 volt across the coil, then you have a 1 Henry inductor. And so another way of thinking about inductance is opposition to the change of current, right? So every time that you can switch a current abruptly, and what the inductor will do is it will tend to oppose that. And so basically, it's really a property of matter. You can think about it that way. It's a property of opposing rapid changes in current. So for that solenoid that we just saw, if we had n turns, this is, I believe it's called the magnetic permeability, I think. The permeability of the core. A is the cross-sectional area and L is the length, then n squared times mu times A divided by L is equal to the inductance. So this is like a property of that solenoid. So if you, for every time you double the number of turns, you quadruple the inductance. This is an intrinsic property of the core material. You can't change this, but you can make the core wider to increase its inductance, and you can make it shorter to increase the inductance. So here are a couple of pictures of inductors. I'm not sure if you guys have any in your kits. Maybe you do, but if you do, it will be either a solenoid or a chip. It will definitely not, I don't think you guys have a toroid. So what we saw is if you want to increase the inductance, you can increase the number of turns, use a more magnetic material, increase the cross-sectional area, or reduce its length. So typical values that you'll work with are small. So microhenries in communication systems, so electronic systems. And in like power transmission, you can work up to tens of henries, but those are large inductors. So the core is generally, two common elements of the core are iron or steel. There are other names for inductors, which I don't personally use. And again, here's how the inductors look like. So here the coil is kind of wrapped around this circular shape. All right. So the circuit symbol, it's one of my favorite symbols to draw in the circuits class. It's a limited list. It's like this, looks like barbed wire or something. The important thing is that as with resistors and capacitors, the positive current by convention hits the high end of the voltage drop. So the voltage drops from here to here when positive charge enters this end. And so in this class, we only work with linear inductors. So we always assume that the voltage across the inductor is proportional to the change in current. And so we know that di over dt, we know that V is equal to L times di over dt. That's our like fundamental equation. That's our starting point. We can integrate both sides of that equation now. So we can rearrange and then integrate both sides of the equation to come up with an expression for I in terms of V. Right, so we know that V is equal to the change in current. The voltage is equal to the change in current times the inductance. We can also go the other way. So starting with the voltage, if you integrate it up to time t and divide by L, you get the current. And if there was some initial current at time 0, you have to add that to the integral. So we assume that at the beginning of the universe, so time equals to negative infinity, there was 0 current flowing through the inductor, which I would say is a good assumption. Okay, so this is exactly reciprocal to what we saw with capacitors. With capacitors, we saw that the current was proportional to the derivative of voltage. Here we see that the current is proportional to the integral of voltage. So power and energy. We know that power is always equal to the product of voltage and current. And we know that the voltage is equal to the derivative of current times the inductance. So now let's integrate this across time to get energy. We know that energy is just the integral of power. And so if we integrate L di over dt times I across time, you get this really nice elimination of the dt. And what started out as an integral across time becomes an integral across current, which is very nice because we know how to integrate a linear function. Is just equal to 1/2 I squared. And then we evaluate that at the two limits, at the beginning of the universe and at time t. And we know that the current was 0 at time equals to negative infinity, which means that at time t, the energy stored in the inductor is equal to 1/2 Li squared. So notice that this is an instantaneous quantity. This energy changes from moment to moment and is totally proportional to the current value of I. right? So the energy, in a sense, is memoryless. The only thing that determines the energy storage is the present value of the current, which is interesting, I think. Okay. Hopefully you're following to this point. Some important properties. The most important one is that the inductor acts like a short circuit under DC conditions. So what that means is that if the current flowing through that coil is constant, so it's not changing across time, then the voltage is equal to 0, and that coil is just functioning as a wire, just as a conductor, because the derivative of I is equal to 0. The second one is a little bit more subtle, and that has to do with what happens to different manipulations of the current. So for example, here, the derivative of the current is always finite, right? You're always changing the current in a finite way. Here, though, you have a slope of infinity at time 0, and you have a slope of negative infinity at this time. And so these two are not physically realizable because they would necessitate an infinite value for the voltage. And we know that infinite voltages cannot possibly be produced. And so what the inductor does when you try to do this is it will smooth out the change in current. So it will not let this happen. It will cause the current to go from this point to this point with some time constant. So in a smooth way, usually in an exponential way. And so again, an inductor is something that opposes an abrupt change in the current. So this is possible in real life, and this is not. So the voltage across the inductor can change abruptly, but the current cannot, which again was opposite to what we saw with the capacitor. So we are going to assume that we have 100% efficiency in the transfer of energy between the storage phase and the voltage generation phase. But in reality, we always have some resistive component to an inductor. So there is some energy loss here that is modeled as a resistor in series with the inductor. So we will assume that RW is 0. And similarly, we will assume that CW is equal to 0. So, but in reality, it's just important to keep in mind that there will be some capacitive coupling across the coil ends. Right? So we basically in this course, we assume, so we neglect CW and we neglect RW. But in reality, every inductor will have a little bit of kind of heat loss at this resistor, and it will have a little bit of a charge that gets built up across the ends of the coil. All right. The current through a 0.1 Henry inductor is equal to 10t times e to the minus 5t amps. Find the voltage across the inductor and the energy stored in it. So who can help me how to figure out the voltage across the 0.1 Henry inductor with this current flowing through it? What do I have to do to this waveform?
Differentiate it.
Differentiate it is correct. And what law of calculus will I be using to differentiate that function? Product rule, very good, right? So let's apply the product rule to this current waveform. So first of all, the governing equation is that the voltage is equal to the inductance, which is 0.1, multiplied by the temporal derivative of this current. So we have to differentiate 10t times e to the minus 5t with respect to time. And so the 10 and the 0.1 cancel out, they become a 1. So that makes our life a little bit easier. So all we have to worry about is differentiating t times e to the minus 5t. Okay, so the derivative of t is 1. Leave the e to the minus 5t alone. Then leave the t and differentiate e to the minus 5t. And what you're left with is e to the minus 5t times 1 minus 5t volts. So that becomes the voltage. And so now my question to you is, what is the value of the voltage at time 0, first of all? One. 1 is correct. It is equal to 1. What about at time equals to infinity?
0.
0 is good. Excellent. Right? Because this at time, as t goes to infinity, this term falls to 0 faster than this term goes to infinity, right? This is a linear ascent, descent, but this is an exponential descent. This one gets there faster, right? All right, and then the energy storage, I'll just go through it quickly. It's just 1/2 Li squared. So it's 1/2 times 0.1 times the square of this function, which is 100t squared times e to the minus 10t. And all of that reduces to 5t squared times e to the minus 10t. All right, any questions as to how we solve this problem? Excellent. The current through a 1 millihenry inductor is 20 cos 100t milliamps. Find the terminal voltage and the energy stored. So how do I get the voltage, first of all? What do I have to do to the current waveform here?
Differentiate.
Yep, differentiate it. So it's going to be minus 20. That's right, minus 20 sine 100t times 100. Right. So the 0.01, this is the inductance, and then we have to differentiate this. And I'm just sticking in the 0.001 because it's in milliamps. Right. So move all the coefficients to the front. The derivative of cos is negative sine. This term, this is just the chain rule. And when you simplify this mess, you get negative 2 sine 100t millivolts. And the energy stored, as always, is equal to 1/2 Li squared. So just plug in 0.001 for L, square this, and you get a value of 0.2 cosine squared of 100t microjoules. So a very small amount of energy, as you would expect, given the current is equal to 20 cos of 100t milliamps. Okay. These are pretty straightforward. Let's move on to finding the current given the voltage. So far we've been finding the voltage given the current. Now we have to find the current given the voltage. So we're given that after time t, so before time t, the voltage is 0. So that's our starting point. And after time t, the voltage has a time course of 30t squared. And we are asked to find the energy stored between 0 and 5 seconds. So what do I have to do to this voltage equation to get the current? Integrate. Thank you. You guys are ready for that one. So what's the integral of 30t squared? Someone's had enough. Yes, very good. 30 times t cubed over 3, which is 10t cubed. Right. So, and then we divide by the 5, 1 over L. Our starting voltage is 5, right? Sorry, is 0 because it's given to us. So this becomes 6t cubed over 3. Or 2t cubed. And then between 0 and 5, that becomes, sorry, fine, right. So this is the value, actually, this is the value of the current at any time point after 0. And actually before 0. This equation holds for all time. And actually, that's not true. This equation only holds for positive time, right? Because we started the integral at 0. Now we have to get the energy stored between 0 and 5. So we have to integrate this equation. So we have to integrate the product of voltage and current from 0 to 5, right? So the product, remember that power is voltage times current. The voltage is 30t squared. The current is 2t cubed. You multiply those together, you get 60 times t to the 5th. And we have to integrate that between 0 and 5 seconds. And when you do that, you get a value of 156.25 kilojoules. Okay, is there any questions about how we go from voltage to current? Okay, excellent. For an inductor, yes, the integral of voltage is current, and you have to also divide it by the inductance. All right, let me see what's next. We could have also used the 1/2 Li squared formula, like 1/2 times 5 times the square of 2t cubed, right? Where t was equal to 5. That would have also gotten us the same numerical answer. All right. So one more problem where we are given a voltage and we are asked to find the current at time equals 4 seconds and also the energy stored in the inductor between 0 and 4 seconds. Okay. So we have to integrate the voltage and add it to the initial current. So here we have a non-zero starting condition. It's given to us. So this, we know that the current flowing at 0, at time 0, is 2 amps. So whatever accumulates between 0 and 4 seconds will have to get added to that initial current. So let's plug in our voltage waveform, which is 10 times 1 minus t. divide that by L. And let's evaluate this integral at t is equal to 4. So we stick the constant out front. We move the 10 in front of the integral, and the integral of 1 minus t is equal to t minus t squared over 2. And we evaluate this at the integration limits of 4 and 0. When you do that, you get 2 plus minus 20, which becomes negative 18 amps. Okay, so now how do I figure out the energy stored in the inductor between 0 and 4 seconds? What's my equation for energy storage through an inductor? One half Li squared, right? Yeah. I'm just doing it on my calculator here so I don't have to advance the slide. And see what we get. So our value for I of 4. So actually it's 1 half Li squared is the, yeah, this is actually a tricky one. So I'm going to write this out. Text. So 1 half L times I t squared. Okay. So energy, what's the energy stored at time 0 in this problem?
Two joules.
Yeah, so it will be, I think it's 4 probably. So 1 half times 2 times 2 squared is equal to 4 joules. That was very close. And then the energy stored at time 4 is equal to 1 half times 2 times negative 18 squared. Right, this 2 here is the inductance, and this 2 here is I0. So this becomes 324 joules, and therefore energy stored between 0 and 4 seconds is equal to 324 minus 4 is equal to 320 joules. So let me get rid of, right, because we had an initial storage of, we had initial current of 2 amps, which means that the inductor had some energy stored in its magnetic field at time 0. Okay, so you want to use this equation for energy storage. Okay, is there any questions about this one? It's a little bit tricky with the energy storage because we had a non-zero initial condition here. All right. Let's move along. Let's get to some circuits now. Okay. So remember that a capacitor in DC conditions was equivalent to an open circuit. An inductor under DC conditions is equivalent to a short circuit. So we are told that in this circuit under DC conditions to solve for I, for V of C, so that's the voltage across the capacitor, and I of L, which is the current through the inductor. And part B is to find the energy stored in the capacitor and the inductor. So the first thing that you want to do here is to draw this circuit under DC conditions. So who can tell me how the circuit will look under DC conditions? What will I have to change?
So it's capacitor becomes an open circuit, correct?
That's
you
right.
would get rid of that branch right there, and then the inductor would just become a straight
Yep,
wire.
exactly. So this 4 ohm resistor becomes dead. And effectively, this is just a 1 loop circuit that has a 12-volt battery in series with 6 ohms of resistance. So my question to you now is, what is the value of IL here? Or what is the value of I, first of all? You have an answer on the chat. 12. How did you get 12? What about the 5 ohms here? Right, so this battery senses, yeah, so it senses the 1 and the 5 together, which are in series. And so the current that comes out of this battery is equal to 12 volts divided by 1 plus 5, so 2 amps. And that is equal to IL, right? Because yes, I is equal to IL here. They should make a feature so that people teaching the chat window will just kind of be off to the side, so I don't have to keep moving it around. So yeah, I is equal to IL is equal to 12 or 1 plus 5. Now, let me ask you, what about the value of VC? What is the value of VC? I like this question. Kind of forces you to think.
Shouldn't it be 0 since it's an open circuit now?
That's a common answer, but it's actually not 0.
What if
Because there still is a, notice that this point here is sitting at whatever the voltage this here is. And this point here is sitting at ground. So VC will still be a live voltage, right? It's whatever the voltage is. It's the difference between this point and this point. So it's actually equal to what?
would it be equal to the voltage coming out of the 1 ohm resistor?
Very close, but not quite. Oh, actually, depending on how you, so the voltage drop across the 1 ohm resistor is equal to 2 volts, correct? Because 1 ohm times 2 amps.
Yeah.
And so then what is the relationship between that 2 amps and VC? If we apply KVL starting from this point around this loop, right? Let me just try to, I'm gonna lose my cursor, but whatever. So minus 12 plus, this is the voltage drop. We said voltage drop here, we said it was 2 volts. There's no voltage drop across the 4 ohm because there's no current flowing through here, plus VC. Is equal to 0. So what does that make VC?
10 volts.
10. Yeah, another way of viewing at it. Another way of, sorry, come on. What's the magic recipe? Another way of viewing it is that VC is in parallel with the 5 ohm resistor, right? Because its terminals are at the same voltage, it shares its terminals with the 5 ohm resistor. So the 5 ohm resistor has a voltage drop of 2 amps times 5 ohms, which is 10 volts. We're coming out the positive end for the voltage source. Yes, that's right. So it's a rise from here to here. And then drop across the 1 ohm resistor and then drop across VC. This is like when you hear the term, that's a live wire. It's referring to a situation like this. So there's no current, but if you pick up those live wires, unfortunately, you will have current passing through you because that is a voltage. It's just that there's no path for that, for that charge to flow through, right? So this is a live wire. It's minus 12 because voltage rises are treated as negative when you do KVL. It has a different polarity. If you're going clockwise, you're going negative to positive, but here you're going positive to negative. So in KVL, we treat voltage drops with a positive sign, and we treat voltage rises with a negative sign. All right, so we have I, we have VC, and we have IL. We just need to know the energy stored in the capacitor and the inductor, right? So we know what the answer for the capacitor is already here. The equation is 1/2 CV squared. So VC is equal to 10 volts. So the capacitor is storing 50 joules. What about the inductor? How much energy is stored in the inductor?
It would be 1/2 L to, well, the volt in current squared.
Yep, exactly. 4 is correct. Okay, so it's 1/2 Li squared, and both L and I are equal to 2, so the answer is 4 joules. All right. Okay, let's continue to combining inductors in series and parallel. And this is really easy because this follows the laws of resistors. So if you know how to combine resistors, then combining inductors is straightforward. And the way we derive that, as always, is just to write the KVL and KCL equation. So let's consider the following circuit where we have a voltage, this can be a battery or whatever, connected to a bunch of inductors in series. We know that this V here has to equal to the sum of the VIs. Okay? So this source voltage here is equal to V1 up through Vn. We also know that each of these is equal to L, their respective inductance, multiplied by the derivative of I. And crucially, this I here is common to each of the inductors. And so the derivative of I factors out. Okay? So you can remove it as a common factor. And then what you see here is that the equivalent inductance just becomes the sum of the individual inductances. So super easy. Reducing inductors is just, you do the same thing as you do with resistors. So the equivalent inductance is equal to the sum of the individual inductance. Now, what about in parallel? So again, we always start off with either KCL or KVL. In this case, we're going to use KCL. We know that the current that's flowing into the circuit, and here we have a bank of N parallel inductors. So we know that the current flowing in has to equal to the sum of the N branch currents. Each of these inductors here is sitting at the same voltage V. That's important. And so what we're going to do is we're going to write the KCL equation at this spot. And remember that the current that is flowing through an inductor is the integral of the voltage. And that voltage is common to each of these terms. And so that can be factored out as, you know, as we saw before. So this current I is equal to a superposition of integrals. And each of these integrals has a starting condition, has an initial current. And in many cases, that initial current will be equal to 0. But we included here for rigor's sake. And so we're going to factor out the integral of V. And what's left in the parentheses here is the sum of reciprocal inductances, which means that our equivalent inductance is the inverse of the sum of reciprocals. So it's hard to say, but again, it's not a difficult concept. It follows the same rule as resistors in parallel. So inductors in parallel follow the same simplification rules as resistors in parallel. And so, for example, if you have two inductors in parallel, then their equivalent inductance just equals to product over sum. Okay, that's straightforward. So here's a table that is very important for you guys. I mean, I don't think memorization is the right term. I think in some sense you'll have it memorized, but if you've studied the material and if you've done a lot of practice problems, then these will become etched in your mind. So you do definitely have to memorize this, and this. Those are foundational, and everything else kind of flows from there. Some important parts of this table. So at DC, a capacitor is an open circuit, whereas an inductor is a short circuit. A capacitor will resist abrupt changes in voltage, whereas an inductor will oppose abrupt changes in current. And in lecture 7 and 8, we'll actually see the mathematical description of that opposition. Resistors and inductors have the same rules for combining, whereas capacitors have the opposite. So two capacitors in series behave like resistors in parallel, and two capacitors in parallel behave like two resistors in series. Power is always equal to voltage times current, which means that for a resistor, it's I squared times R or V squared over R. Whereas for a capacitor, it's 1/2 CV squared, and for an inductor, it's 1/2 Li squared. So the at DC means when the circuit is sitting there and there hasn't been a change, it means not changing with time. DC means not time varying. So you have a battery that's been sitting at the same voltage for a very long period of time. So in lecture 7 and 8, when we move to AC circuits, you'll see that these elements, namely the capacitor and the inductor, their behavior depends on the past. And so there's a dynamic component to the voltages and the currents. All right, let's do a couple of these before adjourning for the day. Let's find the equivalent inductance of this circuit. We're looking from the left, and we're looking into this bank, this network of inductors. Who can help me figure out the equivalent inductance of this circuit?
I can try.
Sure, go ahead.
So first, the 4 Henry and the 8 Henry inductors, they're in parallel, so you could just add them up.
So they're actually, the 4 and the 8 are actually in series, but I wouldn't start there. Let's focus on let's start on the other side.
Okay.
So the 20,
The 20 and the 12 are in series.
right, so that becomes,
So that's 20 times 12 over.
no, remember that inductors behave the same way as inductors behave the same way as resistors. So the 20 and the 12 just add up to be
Oh, okay. So they just add up to be 32?
32, yeah. Plus the 10 gives you
42.
42. And that 42 is then in parallel with
With the 7.
the 7. So 42 in parallel with 7, I believe, is 6. If memory serves me right. So all of this here that I'm highlighting with my cursor reduces to a 6 Henry inductor. So
Okay.
it's 4, 6, and 8.
Okay.
Yeah, so there's some people answering on the chat. So yeah, it becomes 18 Henry. Yeah, so this is just an explanation of what we just did. Okay. All right, calculate the equivalent inductance for this ladder circuit. So again, we want to start on the right side. So what's the first step I gotta make? You can answer on the chat or over the mic.
The 40 and the 20 micro.
Yeah.
That
Yeah,
becomes 60. And that's
Yes.
in parallel with the 30.
Becomes,
I think it's 20.
yeah, 60, and that's 20, yeah. So
Okay.
this whole thing here is 20.
And that's in series with the 100. So that's 120,
Yeah,
which is in parallel with the 40.
and that becomes 30.
Okay. You add that with the 20. So that's 50.
Yeah.
Then it's in parallel. So that becomes 25.
Yes, very good. And there are a bunch of people in the chat that also were giving correct answers. So props to you guys for participating. The answer is 25, right? So the 40 and the 20 give us 60. 60 and the 30 in parallel give you a 20. 20 and the 100 make 120. The 120 and the 40 give you a 30. 20 and the 30 give you a 50. 50 and a 50 give you a 25. All right, I'm gonna stop it here. So we're doing well on time. Homework 3 is posted. Midterm is on April 12th. If you haven't given your, if you haven't signed up for a doodle slot to pick up your circuit kits, please do that immediately. That's super high priority. Start on homework 3. It's a good way of it's like very efficient. If you do the homework early or studying for the midterm and doing the homework at the same time, you kind of saw what your midterm will look like. The signing up for is if you're getting your circuit shipped to you, disregard it. If you're picking up your circuit kit, you have to sign up for a day to meet the TAs. What else? Is it sunny in New York? Good.
Yeah, it's really warm right now. I'm loving
Yeah,
the
it's
weather.
beautiful here, man. I hope you guys get a chance to go outside and enjoy this. Yes, the midterm is until lecture 5 inclusive, so it includes lecture 5. So op amps will be on the midterm. And you'll get a chance to practice your op amp skills with homework 4, which will be released before the midterm, but will not be due until a little bit after the midterm. So you'll have a chance to practice, but you won't have the solutions. Yes, lecture slides 1 through 5. You're gonna love it. I think it's only worth 30% of the grade. I think it's 30, 30, 20, 20 in this course, something like that. Don't quote me on that because I know I've changed it. Okay. You'll be fine. Your head will be fine. You have a question about the capacitors? Sure. Go ahead. This one? Let me just pull up my, oh, I haven't shared my screen. Let me share my screen. Do you want to ask your question?
Yeah,
Mr.
Professor,
go ahead.
it was from the capacitors, the last example.
Oh, capacitors, my bad. Can you tell me which slide number?
I don't remember the slide
Okay.
number. It was a practice question. Yeah, this one. So
Okay, great.
Professor, we already found the charge in the beginning, right? And that charge was for the whole circuit, right? So why do we find a second charge for the right side?
Yeah, it's a good question. The reason is because remember, charge behaves like current. So when the current gets to this point, some of it will take this path and some of it will take the outside path. So you need to know how much takes the outside path.
Okay.
We found the charge is coming out of this battery, but not all of that charge will make its way to capacitors 3 and 4.
So for the previous example, the example before this one,
Yeah.
we did not divide the charge. Was it because they were asking for the combined voltage, like the V3?
Yes, exactly.
Okay.
So V3, all 3 voltages are, let's see, the difference was, let me just take a look at, just to make sure I don't say anything that's misleading. Okay, so let's look at this. Here we're solving for V1, V2, and V3. So V1 and V2 are going to see all of the charge, right? Because they're in series with the battery. Now V3 is common to these 2 capacitors.
Okay.
So if you find, so the way that we found V3 was just by applying KVL, right? We found that V1 is 15 and we found that V2 was 10. So we know that the remaining voltage, the voltage from this point to this point, has to be 5.
Yes.
Right? And so that applies to both of these capacitors because they're in parallel. Whereas in this problem, the 2 capacitors are not in parallel. They're in series. And so their voltages are not guaranteed to be equal.
Okay. Makes sense. Thank you so much.
You're welcome. Any other questions for me? Okay. I'll see everybody on Wednesday. Enjoy the sunshine.